So now that we understand Hooke's law, we can use it to start calculating the amount of elongation, also called deformation, that we can expect from an axial loaded bar. Once again, as I'll repeat again and again in this chapter, this is only going to work when we elastically deform the bar. Because once we plastically deform it, Hooke's law doesn't apply anymore. So let's take a look here at this bar. Now, this is a very generic bar because we want to take a look at everything. So everything is changing in this bar that I've got. You can see the load from one side to the other side. It's changing. So as I look in the X direction, I have a changing load. You can see it's kind of a little conical shaped bar. So I have a changing area that's going through this. So let's take a look at this in context of integration. So if I look at the small element dx in the bar, then I can sit there and go, okay, well, my stress value is going to be the load as a function of x divided by the area as a function of x. And I'm also looking at my strain. Now my strain, because remember, what is strain? Strain is the deformation divided by the length. And so I'm looking at a differential element strain, so I'm looking at d strain dx. So if I take a look at that, I can calculate out what's going on because I can plug this into Hooke's law. Remember, what does Hooke's law say? Stress is equal to modulus elasticity times strain. So if I go and do that, my stress is load as a function of x divided by area as a function of x is going to be equal to E times my deformation as a function of x. So if I take a look at this and I want to know what my deformation is, I can split the variables and whatnot. So my deformation is going to be the load as a function of x dx divided by my area as a function of x times E. And let's just rewrite this here on the new slide because we're going to play around with that. So the change in deformation. I'm sorry, I get sloppy a little bit with my deltas when I'm writing. P is a function of x dx divided by A is a function of x times E. So this is the equation for deformation. And in fact, if we integrate that from 0 to L, that is technically right here the equation for the deformation in a bar. So with this, oops, sorry, I grabbed the wrong mouse. With this equation, we can solve any axial loaded bar. But we have to do a little bit of integration to do that. So let's make some assumptions to kind of simplify this just a little bit. And so basically, if I look at this, what I have is I've got two guys here as a function of x, my p and my area. So on top of that assumption that we're making that we're in the linear elastic region, let's assume that we have a constant force. Once we have a constant force, this guy right here is just going to become the load because it's no longer based on the way that the force changes in x. And then we're also going to make a constant cross-section assumption. So we're in the, and what happens there? Well, this A is no longer a function of x. And so what we are left with is we have the integration from 0 to L of delta is going to be P dx over AE. And then if we run that integration from 0 to L, we get the deformation is PL over AE. So this is for an axial loaded bar. It has a constant force, constant cross-section, and it's in the linear elastic region. Once it plastically deforms, we can't use this equation. If I have a variable force, I can't use this equation. I have to go back to this guy right here. If I have a variable cross-section, I have to go back. The interesting thing about deformation is an additive property. So if we've got a bunch of constant force, constant cross-section bars stacked together, I can sit there and calculate out the overall deflection of the entire thing by doing the sum of all the PL over AEs. So I can do each one individually, add them all up, and go, okay, this is the total deformation in the bar.